Hi, and welcome back to the last section of this course about advanced topics of deep learning. This section will be divided in 4 different videos. In the first one, we will learn more about one of the major adage of deep learning and machine learning systems, which is debugging. Then, in the second video, we will understand why GPU and multi-GPU computing is useful for deep learning applications and how it is possible to parallelize your application through data parallelism or model parallelism. In the third video, we will finally compare all the available packages in R for deep learning and artificial neural networks with respect of all the algorithms we have encountered in this course, so that with a quick look, you can choose the right package for you and for solving your own problem. Finally, in the last video, we will see, for some of you who may be interested, the future directions and open questions of deep learning research. So let's move to the first video of this section, debugging deep learning systems. In this video, first of all, we will understand why improving and debugging machine learning systems is particularly hard and what we can do with our deep learning system if we do not trust our final results. Then we will introduce some basic tips in order to rapidly detect your bug and fix it in an incremental way. So the difficulty is that machine learning is a fundamentally hard debugging problem. Debugging for machine learning happens in essentially 2 cases. Not just when your algorithm doesn't work, but also when your algorithm doesn't work well enough. And what is unique about machine learning is that it is exponentially harder to figure out what is wrong when things don't work as expected. So let's say, for example, we are in this scenario. Your algorithm is defined exactly like the algorithm you read in a particular paper, and it also compiles, and it gets 85% of accuracy on the original dataset. But the paper says it should be 91%. So it's not working, or your evaluation is wrong, or his evaluation is wrong. In the image here on the right, you can see the 3 principal axes of errors your model can suffer from. The first one is the correctness of the program with respect to what we have actually in mind. For example, an incorrect gradient computation or weights update, and so on and so forth. Then we have on the other axis the correctness with regards to the algorithm, for example regarding the choice of the optimal learning rate, using the right formulas for the gradients, and so on. In the end, we have also the model correctness, for example regarding the capacity of the model and the regularization. Debugging and improving deep learning models is even harder, essentially because of the size and complexity of the model. In fact, this is generally much bigger than in simpler machine learning systems, as we have seen during this course. And then consequentially, the time needed to train the algorithm is much bigger, and we have very long waiting times. But also because of the reduced task pipeline in favor of end-to-end models, which, if on one hand is a great advancement, on the other hand means that the identification of the problem is much more difficult. The only way out here is writing more tests as possible for each of the dimensions introduced before and using the following orthogonal approaches, for example. The first of all is start small. That is, before scaling to bigger models with better capabilities, try to reduce your implementation to the smallest amount of code as possible and apply it to a reduced small dataset. This will help you identify the eventual problem very quickly. Then you can start to incrementally expand both the model and the training set. Another common approach is to use synthetically generated data, which are simpler to predict. For example, you can add to your input vector the value of the exact output you would like to predict, so that if well implemented, your algorithm should easily discover this exact linear correlation between your x and y pairs. Finally, especially for the implementation correctness axis, I would suggest you to use the standard debuggers or to be very verbose in your program in order to be well aware of the impact of each algorithmic step along the way. In the end, as a final suggestion, since time is precious, you should generate bug hypotheses, write well-designed tests which can't miss them, and iterate as much as you can.